Welcome back to Biomechanics on Catalyst University. My name is Kevin Tokoph. Please make sure to like this video and subscribe to my channel for future videos and notifications. In this video and the next, we're actually going to look at a biomechanics problem in which we're going to be asked to calculate three things using the torque at the elbow joint. We're going to be asked to calculate the force exerted by the elbow flexors, and usually we just say the biceps brachii, and then calculate the mechanical advantage of the biceps brachii, and then calculate the joint reaction force associated with the elbow in this hold. Okay, so let's first look at the problem. So we've got this guy, this is his right arm, and he has his elbow bent to 90 degrees, and he's just holding a ball in his hand. And what we want to do is we want to calculate the force that is exerted by, in general, the elbow flexors, but the biceps brachii, in order to hold his forearm and the ball in that position. And so this is going to be a torque problem, okay? So here's a few things about this. Peeling away all the skin and all that stuff, just looking at the bones. Right here, this B, this force being exerted directly perpendicular upwards, this is the force exerted by the biceps brachii. Now, just a little basic stuff here. Remember, the biceps are going to attach to the forearm via a tendon, but basically the biceps are going to pull on the tendon, which pulls on the bone to keep it supported upwards. So this is going to be the force vector for the biceps pointed upwards. But then we have the weight of the whole forearm. We're going to assume the weight is 8 pounds. That's the entire weight of the forearm, bones, skin, everything like that. Okay? And then we've got the weight of the ball, which is 40 pounds, and that's being held in the hand. Okay? The other thing also is we have the distance between the tendon of the bicep and the axis of rotation, which is the elbow joint itself. This distance is going to be 4 centimeters. That's the distance of the biceps brachii. This distance of 4 centimeters, this is going to be our distance of the bicep brachii, or DBB. Then we have the ball over here, which is held in the hand. It's 40 pounds. And the distance between the axis of rotation and the center of mass of the ball, which is all this right here, is going to be 35 centimeters, and that's what we're going to call D ball. Again, the distance between the axis of rotation and the center of mass of the ball. Then we have the forearm, and this is going to include the bones, the flesh, the muscles in here, all that. And the weight of the forearm itself is 8 pounds. And the distance between the center of mass right here of the forearm and the axis of rotation is the second line right here. That is our D arm, the distance of the arm, and that's going to be half the length of D ball. In some kinds of problems, they'll just straight up give you a number for this. But in this case, they're telling you it's half the length of D ball, which is 35 centimeters. And we could actually say that's 17.5 centimeters. We'll see that in just a minute, okay? We need to know two things for this problem. One, that each individual torque is equal to the perpendicular force times the distance from the axis of rotation, okay? And then if we add up all the torques, they have to be 0. And really in any introductory biomechanics course, you're dealing with static equilibrium, so the elbow's just held there. It's not moving, it's not rotating. So the sum of the torques will always be 0, all right? And if we think about this, the biceps are going to tend to create a torque upwards because the force is exerted upwards. The bicep is what keeps your arm from rotating downwards. So you don't rotate your arms down like this because the bicep is producing a torque upwards, okay? But the forearm and the ball itself are going to tend to produce a torque that goes down. They're going to tend to rotate the forearm downwards because they're going to be subject to gravity, right? So we're going to have two negative torques, and then this one from the biceps will be positive, all right? So let's look at it. The sum of the torques have to be 0. And if we add all these torques, first of all, let's put it in symbolic form. We have the force of the arm times the distance of the arm. That's going to be this forearm weight right here, okay? And it's negative. And we add on the next term. We have the force due to the ball going downwards times the distance from the ball to the axis of rotation. This one's also going to be negative because it's tending to produce torque downwards. And then our last one is the force due to the biceps brachii times the distance from the biceps brachii to the axis of rotation. This one's going to be positive because it's producing a torque upwards to hold up the forearm. Now we have to do two other things. We're actually going to have to determine the force of the ball and the force of the arm in newtons. We generally don't want to leave these in pounds. Okay. Now, first we deal with the ball. It's 40 pounds. The way we can convert this to units of newtons is by multiplying by 9.81 meters per second squared and dividing by 2.2 pounds per kilogram. If you're ever given pounds, this is always how you convert to newtons. And so the 40 pounds of the ball is going to be equivalent to 178.36 newtons. We're going to do the same for the weight of the forearm. It's 8 pounds. We multiply by 9.81 meters per second squared, that's G, and then divide by the conversion factor, 2.2 pounds per kilogram. And we get that the force of the arm, which is a weight pulling downwards, is 35.67 newtons. Okay, so we've got these in newtons right now. Let's go ahead and plug in these numbers, and then we'll rearrange it and solve for the force due to the biceps brachii. So now I've got 0 equals, this is because I'm adding up the torques and they have to sum to be 0. 0 is equal to, let's do the ball first. The ball, we calculated its force was 178.36 newtons. So 178.36 newtons times the distance from the axis of rotation. Well, this distance was 35 centimeters. It's customary to put this in meters. So the way to convert centimeters to meters is to divide this number by 100. 35 divided by 100 is 0.35 meters. Okay? And it's negative because that's producing a torque that's going to tend to rotate the arm downwards. That's going to be negative. Next, we'll do the arm. The arm we determined of having a force of 35.67 newtons times the distance from the axis of rotation. So this 8 pounds of force that's due to the weight of the forearm is exerted at a distance of half d ball, where d ball was the distance from the axis of rotation to the ball. Well, it's half of 35 centimeters, so that would be 17.5 centimeters. And if we convert that to meters, we divide 17.5 by 100, and we get 0.175 meters. All right? And it's going to be negative again because this is a weight and it's going to tend to rotate the arm downwards. Right? Now for the positive term, this is going to be the torque that's positive because the biceps are going to tend to want to rotate the arm upwards. Okay? Because it's a muscle preventing this arm from rotating downwards. So we don't know what the force due to the biceps are. That's what we're asked to calculate, but we do know the distance from the axis of rotation, which is 0.04 meters. Again, the way I determine that is I know the distance between the biceps attachment and the axis of rotation, DBB, is 4 centimeters. So I can divide that by 100 and I get 0.04 meters. Now this is really just a matter of cleaning this mess up. It's really just going to be a bunch of multiplication and then solving for the variable of interest. So if I multiply 178.36 newtons times 0.35 meters, I get this first term is going to be negative because of the negative sign, negative 62.426 Newton meters. Again, an individual torque, any torque is going to have units of Newton meters. And that's from the newtons from the force and the meters from the distance, right? And then I have this negative 35.67 newtons times 0.175 meters. That's going to give a torque from the arm of negative 6.2427, again, Newton meters. Plus the force due to the biceps brachii times 0.04 meters. All right? And this whole thing is still summing to be 0, so I have 0 on the left side. Now what I'm going to do is I'm going to add these two individual torques over to the left side. Okay? So this negative 62.426 and negative 6.2427. I'm going to add these over to the other side. And so when that happens, on the left side now, instead of a 0, I now have the sum of these two, and it'll be the positive form. That's 68.6687 Newton meters. And that's equal to the rest of this, which is on the right side, the force due to the biceps brachii times 0.04 meters. All right? And now the way to solve for the force right here is to divide through by the meters here, 0.04 meters. And so what I'll ultimately get is the force due to the biceps brachii is 68.6687 Newton meters. That's from right here on the left side. And when I divide through by 0.04 meters, I get approximately a force of 1,717 newtons. I'm neglecting significant digits right here, but it's going to be approximately this value. All right? So this is the force exerted by the biceps. All right? And really the elbow flexors in general. So that actually takes care of the force part of this problem. All right? The next thing I'm going to do is calculate what's called the mechanical advantage of the bicep. Okay? The way that you calculate the mechanical advantage, generally speaking, is you're going to use the force that's needed to be lifted. Okay, this is the weight that the bicep is having to overcome, or really the weight that any muscle is having to overcome. And then you divide by the force exerted by that muscle. Okay, so if this was the mechanical advantage of the quadricep, let's say, which we'll actually do that eventually, this would be the weight needed to be lifted by the quadricep divided by the forces exerted by the quadricep. Right? Now, how much force is needed to be lifted? Well, to calculate this, I'm simply going to add these two forces from up here, because the bicep is having to counteract the weight of the forearm plus the weight of the ball. So that's going to be the sum of these two forces, 178.36 newtons and 35.67 newtons. These sum to approximately 214 newtons. We just calculated the force due to the biceps brachii. That was 1,717 newtons. When you divide this out, you get a decimal. It's going to be approximately 0.125, and that's less than 1. Also, understand that 0.125 is exactly the fraction 1/8, so I may use 1/8 from here on out, but 1/8 is less than 1. And this brings up a really important point about the biceps. The biceps are what we call a class 3 lever. Okay, I'm actually going to blow this up for just a minute. A third class lever, or a class 3 lever, is defined as a situation where you have the force that's being exerted, that's the M here for muscle. The force that's being exerted is between the weight, which is over here on the right side, or R for resistance, the weight, and the fulcrum. So it's a little confusing because of the letters they're using. But the point is the muscle, the force that's being exerted, is between the fulcrum, which is the axis of rotation, and the weight being lifted, the resistance. Again, if we think about it in this problem, here's the rotation right here. Here's the force being exerted upwards, and then all the weight is concentrated over here. And so the force is being exerted between the fulcrum, the rotation point, and the weight, all this stuff over here. When you have a situation like that, it turns out to be a very inefficient muscle. Okay? And so what has to happen in order to lift a certain amount of weight, the muscle has to generate way more force just to lift the small amount of weight. In other words, what we're saying is that in order to lift 214 newtons, the bicep has to generate 8 times the amount of force. Another way to think about that, if you were trying to lift 100 newtons of weight, the bicep would have to generate 8 times the amount of force, so 800 newtons. And so the bicep ends up being a really inefficient muscle because of that. That's one of the reasons why the biceps, or the elbow flexors in general, are among the weaker muscle groups. They're, first of all, not a very large muscle relative to the other muscle groups of the body, but they're third-class levers, and so they're not going to be able to lift near as much weight given the amount of force. In fact, as we said, in order to be in a static equilibrium problem, so an isometric hold like this, your biceps have to generate anywhere around 8 to 10 times the amount of force just to lift some small amount of weight. Okay? But this is how you actually calculate mechanical advantage. We'll see a problem later on in another video where we'll look at the gastrocnemius, the calf muscle, and we'll see that's a far more efficient muscle. Now we're actually going to calculate the joint reaction force. Okay? So here's something interesting to think about. When we're doing joint reaction force, this is a force that's exerted directly on the axis of rotation. Okay? So joint reaction forces are exerted directly on the axis of rotation. They're kind of like balancing forces within the joint itself. And so it's important to realize that because the joint reaction force is exerted directly on the axis of rotation, it produces zero torque. Because even though there's some force there, the distance between the axis of rotation and these joint reaction forces, which are given by J, that distance is 0. And so if we think about the torque formula, you'd have a force, but it's times 0 because it's directly on the axis of rotation. So anything times 0 is going to be 0. So joint reaction forces do not generate any torque. And here's why we have to consider them. We're in an isometric hold, okay? Nothing's moving. It's completely static equilibrium, okay? We're not curling or curling the arm up or curling it down. Everything is still. And so in order for things to be still, all the forces have to balance to be 0. So all the forces in the x direction have to balance to be 0. Because if they don't balance to be 0, that means we're going to have net movement either in the right or left direction. Okay? Additionally, all the forces in the y direction, the vertical, have to sum to be 0 as well. Because if they didn't, we'd have net movement either upwards or downwards. Now, if we just consider from the previous problem the force due to the arm, the force due to the ball, and the force due to the biceps brachii, I can guarantee you this. I won't do this, but you should try it. If you were to add up this negative, because it's negative because it's going down, negative 178.36 newtons, and negative 35.67 newtons, and then add 1,717 newtons, I guarantee you, you're not going to get 0. In fact, you're going to get a pretty positive value. And what that would cause is this ball and the arm to be going upwards, but they're not. It's static. So we have to have another force that's adding some force in the downwards direction to keep everything static. And that's going to be the joint reaction force. Now, none of our forces are in the x direction here. We'll do another example in the next video where they are. But none of our forces are exerted in the x direction. They're all vertical. And so we don't even have to consider the x direction here. But we do have to consider the y direction. So to calculate the joint reaction force, and it's specifically the y direction of it, we need to add up these four forces and sum them to 0 because we're in static equilibrium. So 0 equals the force due to the arm, plus the force due to the ball, plus the force due to the biceps brachii, plus the joint reaction force. Okay, I think I did this again where I flipped these two. In any case, let's do the force due to the ball first. The force due to the ball is our negative 178.36 newtons. Then I have to add on the force due to the arm, that was the smaller one, minus 35.67 newtons, because again, that's a negative force. And then I'm going to add on the force due to the biceps brachii, that's going to be 1,717 newtons. And then in order to balance these to 0, there has to be another force here. It's the force at the joint, it's the reaction force, J sub y. And again, this is the joint reaction force only in the y direction. And this becomes a pretty simple algebraic problem. I just need to solve for J sub y. That means adding these two negative forces over to the left side and then subtracting this positive force over to the left side. What that's going to give me is a joint reaction force in the y direction of 178.36 newtons plus 35.67 newtons minus 1,717 newtons. And when I add all these together, we get a joint reaction force of negative 1,502.97 newtons. And what you can do, and you should try doing this, basically take this number, this negative number, this J sub y, and plug it back in here, and add it to these three forces, and you will get 0. And that has to be the case because if the sum of the forces, at least here in the y direction, were not 0, you would have net movement, net acceleration of this ball in the forearm upwards or downwards depending. Okay? In this case, it would be upwards. But to balance it and to make it static, you have to have a compensatory force pointing downwards located in the joint that prevents this upward acceleration. Okay? And so this is your joint reaction force. Now, for all these torque problems that we're going to see in biomechanics, there's a couple really important things that I want to mention. First of all, in the previous video, or if you're watching the full video in the first part of the video, when we actually calculated the force that's exerted by the muscle, in this case it was of the biceps brachii, to calculate the force, you always start with torque. Okay? You start with adding the torques together, setting them equal to 0, and that will allow you to calculate the forces, okay? The force due to the muscle. However, when you're calculating the joint reaction force, you have to use these equations. The sum of the forces in either direction have to be 0. And you'll always calculate this force first. You never calculate the joint reaction force first, because this force will require you to know the force exerted by the muscle. So there's actually an order in which you do all of this. You always use torque first to calculate the force due to the muscle. That's generally what you do. And then once you know the force due to the muscle, then you can go back and calculate the joint reaction force from these two expressions right here. Some of the forces in the x direction must be 0, and the one we used here, some of the forces in the y direction must be 0. All right? So hopefully this made sense. And so now in the past couple of videos, we've now learned how to calculate force due to the biceps brachii in order to hold this isometric contraction. We've also talked about calculating mechanical advantage of that muscle and now calculating joint reaction force. In the next video, we're going to do a problem very similar to this, except we're going to start involving some trigonometry. And one of the ways that we're going to do that is we're actually going to have now the bicep tendon attaching at an angle that's not perpendicular to the forearm. And so that's going to require us to use some trigonometry. We'll also see some more examples where instead of holding the elbow at 90 degrees, we could hold it at 30 degrees or 45 degrees or something like that. So make sure to join us then. As for now, please make sure to like this video and subscribe to my channel for future videos and notifications. Thank you very much.